My title is External Data from Euclid to SKA, sorry. Is a quite confusing title, but it's only an excuse to make another talk about cluster galaxies and various bands. Okay, I'm part of the Euclid collaboration. In particular, I am coordinator of the working package external data within the OU level 3. I'm a coordinator of working package.
Switch off the microphone.
If you want, I can make a more theatrical spoke. Okay, coordinator of working package external data, a coordinator of validation of the science galaxy cluster working group, and part of various working packages. Lucia, Elena already introduced Euclid for me. This is a very big survey limited to JMH 24 with 15,000 square degrees for the white survey. But I remind you what is the level 3, and that the first is housekeeping data, level 1, calibrated level 2, and level 3 is science-ready data. R is part of the ground segment in the sense that data should be done in a semi-automatical way. The definition is that we need to produce science-ready data products, mostly catalogs, but what is important that they are validated, scientifically validated data, and then there was only officially validated data that came from Euclid. And then I am part of the external data. I am responsible for the implementation. Then Martin Kilbinger is responsible for validation. Critical is, as already said by Elena, we need to write programs. We are astronomers, we are not engineers, we are not software specialists, but we have to write in a professional way, very efficient way. We cannot run a program for 2 months for one data. We have no manpower assigned. We have strict deadlines, but remember, and is more for also for the Euclid collaboration this way, that remember that OU level 3 will be the only validated data that are coming out from Euclid. And then there is the possibility that all the science, Euclid science, will be done on this data. I'm responsible for 3 processing functions. One is related to uncertainties in the correction for galaxy extinction, because these affect the analysis of galaxy clusterings, in particular through the covariance matrix. Why? If I show the emission as measured from Planck, you see that there is a variation of emission, of extinction on the scale of some degrees, and this scale corresponds exactly at high redshift to the BAO dimensions. BAO is one of the primary probes for cosmology in Euclid. This is the angular dimension of BAO as a function of redshift. If you are a low redshift, the dimension is small, but if you extrapolate this dimension at higher redshift, the scale, angular scale, matches exactly the dimension of the clouds in our galaxies. This is a problem. The other two processing functions regard clusters of galaxies and point sources in other bands. In particular, why clusters of galaxies are important. Some time ago, but the paper is still in publication phase, we make some forecasts for cosmology with clusters of galaxies. In particular, we computed, in this case analytically with a confirmation from MOX, of the selection function, cluster selection function in Euclid. You can see, as a function of redshift, that Euclid will detect all the clusters down to log m 14. This is important because having in hand the selection function the number counts, the power spectrum of the distribution of galaxy cluster, and the scaling relation, essentially in this case richness versus mass, you can end with a semi-precision cosmology in order to contrast the cosmological parameters with this precision. This is important. But then my task of the external data, we have to correlate the Euclid cluster with external data, X-ray, Planck, or other bands, in order to calibrate in mass Euclid cluster to derive the scaling relation, for example. And then we devised a procedure involving MOX catalogs or semi-realistic MOX, in practice constructing MOX from real data. We need to have an idea of errors in Euclid cluster. This is a work in collaboration with Bella Gamba and Roncarelli. These are the errors in positioning the cluster on the plane of sky and the photometric redshift space. This is the dominant error. We are doing more or less the same in the BSD Kids survey. And then we can start to correlate or to make forecasts for the correlation, for example, in Planck, or for other probes in microwave, or for Rosita. In this case, we need, and we are collaborating with the group of Thomas Rybrecht, we need the dimension of Rosita cluster as a function of redshift, and the limiting mass as a function of limiting flux for Rosita. And then we can make forecast for correlation. This is the redshift distribution of Euclid clusters. In black is the redshift distribution of Rosita clusters, and in blue there is the redshift distribution of the matched catalog. More or less 70% of Rosita clusters are present uniquely in Euclid. But as you can see, that the Euclid will have a high redshift tail cluster above redshift 1. But the problem that we are doing all this job with MOX, but we have no idea what are cluster at high redshift. And then back to Woods, where we are doing, as a collaboration, a stronger search for structure, for protocluster. We found one a redshift 3.3, Olga Kuchati found another one a redshift 3, and then we are studying now a redshift 4.6. They are showing different, very different behaviors. For example, the remote clusters show an excess of massive galaxies and brighter galaxies. This means that galaxies are evolving differently in this protocluster than the background. But for example, in the Kuchati et al. At redshift 3, these properties are not present. Other bands, jump to radio, evolutionary map of the universe. This is SKA precursor. With Tiziano Venturi is the PI, and we have the SKA in OABo. We have an early science project within the MLU about Shapley. The title is Radio Emission in the Shapley Concentration for Galaxy to Cluster and Intercluster Scalar Radio Emission. These are the science goals. Essentially, we want to see AGN and extended emission due to emerging cluster. Why Shapley concentration? Because since several years we studied this huge overdensity. Then we is an ideal place to study the astrophysical effect of cluster merging. We already published 21 referred papers on this region. This is visible in X-ray, in optical, and now also in Planck. In the past, we studied these merging structures from the radio-optical luminosity function with GMRT and ATCA data. In particular, we found that emerging clusters tend to suppress the AGN activity. And then we studied also, we found a radio halo in related to minor merging in this sense. And then we are doing a construction of merging trajectory using the cluster weather when the cluster weather are acting on extended radio sources. At the moment we are collapsing all the existing data we have taken in the past, essentially GMRT data with ATCA data and VLA data in order to have a global vision of this merging. In particular, we detected a possible relic between these clusters. Parallel to this, with the Tiziana, we are making observation with the Murchison Whitefield array in Australia and the CAT7 Mercat precursor in South Africa. Point sources, directly to point sources from Euclid to SKA and the SKA precursor, because we presented our work in synergistic science with Euclid and SKA, Bardelli, Ciliegi, and Salvato. We cross-correlated the incoming Euclid catalog with the SKA Pathfinder, and we find that there is a problem in the SKA Pathfinder, essentially is the resolution. The resolution will increase the number, the percentage of spurious identification and decrease the number of identification. But projecting all our work to SKA, we can predict the percentage of Euclid star-forming galaxies present in SKA as a function of the limiting flux of SKA, and we found that if the continuum survey of SKA will be 0.2 micron Jansky, this is the green line, 99% of the star-forming Euclid galaxies will be detected in radio. This is a good thing because the radio emission is a tracer of star formation that is independent from the dust. But the problem is, what is the star formation at a higher redshift? We don't know, and then we have to rely on observation. Back to Woods, once again. What we found from Woods is that at high redshift, the specific star formation is evolving flatter than the models. In particular, there is a specific redshift, a threshold redshift, a redshift 2, where the real galaxies are evolving faster than models, a redshift less than 2, and the evolution is flatter than models for redshift more than 2. What I mean with models are the cold gas accretion and hydro models. Another thing, interesting things from Woods is that we can make a self-fitting of spectroscopic and photometric data at the same time. In fact, if we make a self-fitting of photometry, for example, in order to determine metallicity and age, there is a lot of degeneracy. But the nice thing is that this fit in spectroscopy and photometry, the error ellipses have different directions, and combining the two, we can hope to decrease the area of the error ellipses. And then we can define the formation redshift function is the number density at a fixed redshift of galaxies forming at a zeta f. This is formation redshift. This function is evolving little, but if we put the formation redshift function as a function of the stellar mass and in bin of redshift, we can see that at high redshift, the formation redshift is more or less constant as a function of stellar mass. A low observation redshift between 2 and 2.2, the formation redshift function is strongly decreasing with stellar mass. This is a clear sign of downsizing. Sizes of the cluster. We make we stacked galaxies as a function of redshift. You cannot see the colors, but this is high redshift. And then we found that although the global area of galaxies at high and low redshift is changed little, we found that in reality what is changing is the light concentration. Galaxies at high redshift are more concentrated than galaxies at low redshift. And this is, for example, the ratio between the dimension of galaxies at 20% of the light and the galaxies at 80% of the light. Okay, and then we can reconstruct using the HOD models with the, okay, this is the last result, that the galaxies at high redshift is very efficient in forming galaxies. Then there is a creation of both M star and halo, due to the merging for M halo and star formation for the M star, and then you stop the growth of M star, and then you continue to grow the M halo. I stop here. Sorry.
One question. I have a curiosity, Sandro. When you show the protoclusters at redshift 3,
Yes.
I've seen a mass, associated mass of 8 times 10
Okay,
to the 4 meters.
It's not a mass related to idealization or relaxation. It's just the mass computed within the over density. Okay? Nothing to do with the value. It's not the typical mass SKA computed for a cluster.
Do you know the size of this region? Is
4 megapascal.
because indeed, it's, if this is the size, it's indeed having a very high total density. And
Yes,
I
10.
wonder, yeah.
10.
Is it? Did you check that this is compatible with lambda CDM
Yes.
predictions, even video area,
Yes,
statistics?
yes. We use the simulation, under simulation, in order to estimate the mass in practice.